Welcome. We are discussing the secondary steel making. Already we have taken 2 lectures. It is the third lecture, that is the module 8. And here I will talk about the vacuum techniques for refining steel. So, the concept that will be covered here, what is the role of vacuum in refining, and then I will talk about the degassation kinetics and degassing thermodynamics, and then degassation thermodynamics, kinetics, and then inclusion decomposition under vacuum, distillation of elements under vacuum, and the vacuum practice in secondary steel making. So, role of vacuum in refining. Why? What is the role of vacuum in refining? Basically, some dissolved gases, that is the gaseous impurities like hydrogen, nitrogen, and oxygen. Basically, these are the three major gaseous impurities in liquid steel, and they have very limited solubility into the solid state. Liquid iron can accommodate a lot of gaseous impurities in their structure, which when you solidify it in the solid steel, their solubility is very low. As a result, during solidification, so they will be ejected from the liquid steel at the solid liquid interface. So, as I said, that is, it will give a lot of supersaturation of those impurities at the solid liquid interface, and they can precipitate very undesirables, nitrides, hydrides, and oxides inclusions. Okay. So, that is one thing. And nitrogen, and what the problem they can do, nitrogen in solid steel basically reduces the toughness. It reduces the toughness and the aging characteristics. So, basically if you age it, then nitrogen precipitate, nitride precipitates at the grain boundary, and then they make basically work hardening. When you do the working on the steel, then you require some intermediate annealing, because you have to diffuse out the there is the nitrogen from forming these compounds. Basically, when you are, that is the major important, that is the thing. The solid steel, nitrogen in the solid steel reduces toughness and the aging characteristics, and also enhances the stress corrosion cracking, because if the nitrogen gas pressure increases inside the voids, and that can enhance the stress corrosion cracking. And more importantly, there is a strain hardening effect of nitrogen does not allow extensive cold working. Basically, if you want to do the cold working, then you have to do the intermediate annealing. Repeatedly annealing you have to do, such that you have to disperse the nitrogen away from supersaturation and segregation at certain location and making some precipitates. That basically adversely affect the strain working. Okay, strain hardening become very high, and then it can develop brittleness, it can develop cracks and all these things. So, during some cold working you have to do annealing such that you can disperse the nitrogen within the matrix uniformly. Otherwise, nitrogen concentration at a particular segregation at a particular location, and then precipitates makes all these problems. So, you cannot do any deep drawing purpose. Suppose you want to do the deep drawing with the nitrogen in steel, you cannot do that, because nitrogen, all these precipitates, nitrogen precipitates at the grain boundary makes this working, strain hardening very difficult. It is hardened very fast. It hardened very fast, strain hardened very fast, and that is develops a lot of cracks and all these things. As a result, for deep drawing purpose, you cannot use, because when you want to reduce the thickness to a very low level, then it's a problem. You cannot do that. In that case, nitrogen basically develops some crack formation and all this. These problems are there. So, it will brittle, and then you cannot do the deep drawing. It will form the cracks, and the sample will be rejected. So, hydrides, similarly hydrogen forms some hydrides, and hydrides are not very stable. So, they basically dissociate into hydrogen, and the hydrogen gas can build up inside the pores, and then they can make a pressure, and then that can lead to cracks, especially if it is near surface region. They can make the hairline cracks. Or if the hydrogen, that is, as the hydrogen in the pores increase the pressure, so as a result they can lead to the stress corrosion cracking also. It can assist in the corrosion also by pressure, that is called the stress corrosion cracking. So, then this is hydrogen as a problem. Hydrogen of course has a very high diffusivity. So, as a result, when you want to make a very thin sheet, then the hydrogen will diffuse away to the atmosphere. It's not a problem because of very fast diffusion. If you want to make a very thin sheet, because in case of the thin sheet, since the thickness is less, hydrogen can easily permeate through the structure and diffuse away to the atmosphere and not make too much of problem. That's why that is when you make thin sheet by processing of rolling, then hydrogen doesn't make that much problem because with very high diffusivity and the thickness is less, then it can easily diffuse away from the steel. So that doesn't make too much of problem, but problem comes if you want to forge something. So a big object if you want to forge and you have hydrogen in it, and then it is a problem. Then, so however, in forging of large size, hydrogen may be released in the pinholes and may cause the surface crack assisted by stress during forging, because you don't allow the hydrogen to diffuse away in that case, because large object is difficult because long distance it has to traverse, so it cannot come out of the structure, and then it remains entrapped hydrogen gas, and then assisted by the stress they can lead to crack generation at the surface. So all these gaseous impurities like nitrogen, hydrogen and oxygen really poses some problem. Hydrogen, for example, hydrogen, that is the surface airline surface cracks and stress corrosion cracking. Nitrogen also does the same thing, but nitrogen is more problem for deep drawing purpose. If you have nitrogen, you cannot use it. It is very well known. You cannot deep drawn a steel where nitrogen is more. Okay. And oxygen, obviously, you know, a lot of undesirable oxide. Beside oxygen also can form the blowholes in the form of carbon monoxide, as I discussed last lectures also. So those problems are there. So all this gaseous impurity has to be bring down to a very low level, not only for casting point of view, but also post casting in the downstream application also. This nitrogen, hydrogen, all this can make a problem during the further processing of liquid steel. Further processing of the solid steel, I am telling. So then also this hydrogen, nitrogen make a problem if you don't control their amount significantly in the upstream processing. So you have to bring down these gaseous impurities as low as possible. Okay, now how the vacuum can help in, because vacuum, dissolved gases in liquid steel you can reduce to a very low level under vacuum. Obviously, all these dissolved gases can be reduced under vacuum because you dissolve, and this is the reaction. You can see any dissolved gas reaction is this. Suppose you have 2H and it will go to hydrogen gas. So under pressure, if you just reduce the pressure, obviously under reduced pressure, this activity will go down, hydrogen quantity will go down, the reaction will move in this direction. So under vacuum, that is your activity of the gaseous hydrogen, oxygen or nitrogen will go down because this hydrogen move away from the system because it is a gas, move away from the system. So this reaction moves in the forward direction. So under pressure, you can make this reaction in the forward direction. So both for hydrogen, nitrogen, and in case of the oxygen, the reaction is little different. In case of oxygen, you have this reaction that is forming the CO gas like this. In case of the nitrogen, so two nitrogen can form the nitrogen gas. So all this reaction will respond to the pressure. So under pressure, you can really bring down to a very low level thermodynamically, as I will show. Kinetically has some limitation with nitrogen, I will discuss. Okay. So these are the things. Okay. Now let us see the thermodynamics of degassing. Now thermodynamics of degassing, you can I have written some. That is the dissolved hydrogen forming the hydrogen gas, dissolved nitrogen forming the nitrogen, and carbon and oxygen combining the CO gas. Okay, these are the relevant reaction, and these are the equilibrium relationship. So you can write, that is the, from the equilibrium relationship you can simply write, that is the activity of hydrogen into the hot metal. This is the activity of hydrogen is equal to Kh into Kh to the power half. So this relation, you know, this is also called the Sievert's law, and Kh is called the Sievert's law constant, which is nothing but inversely proportional to the equilibrium constant. So, and now this activity obviously with respect to the 100% standard state. Okay. Now units, actually you can represent the that is activity, that is the activity is directly proportional to the that is the weight percent of hydrogen if the Henry's law is valid. Now you can write this, if you write this in terms of ppm, that is the concentration, if you express in terms of ppm, then you have this relationship. Okay, simply you can write it in terms of weight percent, or you can write in terms of ppm, and obviously in case of ppm, if you write this, this is the relevant reactions, the relevant correlation between the Henry's law coefficient and the temperature. Similarly, for nitrogen, if you write this nitrogen reaction equilibrium relation like this, and then if you express the Henryan activity of nitrogen in terms of ppm, then the corresponding relationship is this. That is the Henry's law constant. That is your, you can Shiva's law constant, you can say, and the temperature. This relation is like this. Similarly, the other relations are given. This is all the thermodynamic relationship, and if we apply temperature is equal to 1600 degrees centigrade or 1873 Kelvin, and pressure is 1 millimeter of mercury, and that is called the 1 torr pressure, and it is approximately 10 to the minus 3 atmosphere. Okay. So, under 1 millimeter of mercury or 10 to the minus 3 atmosphere, because here if you put this pressure, and kh you can calculate from here, and you can calculate, that is the weight percent of, or the activity of hydrogen in terms of ppm of hydrogen is 0.77. So, simply using this correlation, you can calculate that at 1600 degrees centigrade and 1 torr pressure, the hydrogen amount into the liquid bath can be reduced to 0.77 ppm. It's very low value. Similarly, for nitrogen, you can say you can bring down the nitrogen concentration to 14 ppm. At 1600 degrees centigrade, 1 torr pressure, the dissolved nitrogen, okay, will be only 14 ppm. So, you can lower down the hydrogen and ppm to a very low value, right? And similarly, if you see carbon oxygen, if you just do that, and then also you can find that you can bring it down. If it is in weight percent, this is the weight percent, or in ppm, this is the 40.47 ppm. So, carbon also, there is oxygen. Oxygen can be lowered down to 0.47 ppm, assuming the carbon has 500 ppm. If you have, because it is C, you have a product, that is the, it is the product of concentration of oxygen and carbon. So, if you know the carbon is equal to 500 ppm, so oxygen will be 0.47 ppm. So, 0.47 ppm of oxygen will be in equilibrium with 500 ppm of carbon into the liquid still at 1 torr pressure. That it is what it is telling exactly. So, you can see that you can eliminate the all the gaseous impurities to a significantly low level, right? Okay. Hydrogen and nitrogen can be reduced to 1 to 15 ppm at 1 torr pressure, that we can find. But kinetically, hydrogen not a problem, you can see the nitrogen is a problem. It has been found that if you have too much of oxygen and sulfur into the bath, which are surface active, in that case, the desorption of nitrogen become very difficult from the interface, because oxygen and sulfur are surface active and they occupy the space at the surface. As a result, nitrogen cannot find open space for its desorption to the atmosphere, okay, through which it has to do the desorption. There is the oxygen, the nitrogen from the bath has to come to the surface, okay, and then from the surface it will go to the atmosphere, but it does not find too much of space in the surface. So, nitrogen from the bulk on the space on the surface become very less, as nitrogen from the bulk cannot come to the space, because most of the space at the surface are occupied by the oxygen and sulfur. That is why in practical situation you cannot come down to 14 ppm of nitrogen, especially if you still contain a lot of oxygen and sulfur, and that is why you have to deep deoxidize the bath and deep desulfurize the bath before you go for the vacuum treatment for nitrogen removal. Otherwise, in practice, that is why in practice lowering nitrogen to a very low level become difficult, say 14 ppm or less than 50 ppm become a difficult, especially in presence of oxygen and sulfur. Still should be deep deoxidized or desulfurized first before the denitrogenation. So, if you want to do the denitrogenation to very effectively, you have to first deoxidize or desulfurize the bath, and then you do the denitrogenation. Okay. So this is very important from kinetics point of view. And oxygen can be lowered down, you can see less than 1 ppm in presence of carbon and under vacuum. And one calculation also can be shown that if you don't have carbon in the system, oxygen, that is by this reaction, there is a dissolved oxygen to oxygen gas, this reaction is not very effective. In absence of carbon, you cannot remove the oxygen to a very low level. But in presence of carbon, you can lower down the oxygen to a very low level, less than 1 ppm. But if you don't have carbon in the system and you have a lot of dissolved oxygen, you cannot remove under vacuum, because thermodynamics say this reaction, it will be weight percent will be very high. I have not shown that, but it is indeed the situation. So, but oxygen can be removed in presence of carbon, right? So, this is the thermodynamics and kinetics of degassing. And now next I will come some of the accompanying reaction that take place under vacuum. What are the reactions? You can see some inclusions decompose under vacuum, right? For example, aluminum nitride, it is an inclusion. It decomposes under vacuum to aluminum and nitrogen. Nitrogen is gaseous, that's why it responds to the vacuum and nitrogen go away from the system. For example, silica is a solid impurity. It reacts with the carbon forming SiO gas and CO gas. Both are the gas. SiO and the CO both are the gas. So, under vacuum, this reaction will move in the forward direction, because SiO and CO will move away from the system and this reaction move in the forward direction. So, in presence of carbon, you can easily break down the SiO2 inclusion into the bath. Or you can have this reaction also, SiO2 plus 2 is easily Si plus CO. So, in this case, SiO2 will decompose and it will increase, it will go into the dissolved silicon in the bath will increase. So, and then CO gas it will go away. So, the inclusion can decompose this way. And decomposition of magnesium refractory, magnesia MgO refractory. You can see MgO solid, you can decompose into magnesium gas and the oxygen gas, or magnesium oxide solid plus carbon, it can form Mg gas and the CO gas. And it has been thermodynamically found that this reaction is more probable compared to this reaction. So, MgO in presence of carbon can easily decompose to magnesium gas and carbon oxide gas. Okay. So, the refractory decomposition also possible, but which is not desirable. These are desirable, these are the desirable reaction, but this is not very desirable. So, we have to be cautious about the refractory decomposition. And then several elements are there which are distilled off under vacuum. And one of the main is the magnesium. You can see magnesium, the manganese. Manganese has a high vapor pressure under vacuum, and under vacuum it distills off. Among the impurities, I can show you, that is the manganese has little high vapor pressure and it distills off under 1 torr pressure, 1600 degrees centigrade, and even with 1 weight% manganese in the bath, it can distill off. We will just show those results. So, now this is here. We have calculated the vapor pressure of different elements in steel. Okay, vapor pressure, what are the vapor pressure? We have calculated at different weight%. There is 0.05 weight% or 1 weight% of their presence into the liquid bath. So, how do we calculate this vapor pressure? Because we know the definition of, that is from the definition of activity, you can write like this. So, H, if I say M is equal to Hm, okay. Okay, let us take it little bigger, right. So, activity Hm you can write like this. How do you write this activity? Activity of Hm you can write, that is the, you can write partial pressure of some metal divided by partial pressure. Now, that is the activity of some element, right? M, I am writing the same. Activity of some element you can write, that is the partial pressure of M divided by, in the system, there is the partial pressure of that element in the liquid steel, in the multi-component liquid steel, divided by partial pressure of the element under pure condition, when no other elements is there. Under pure condition, this is partial pressure or the vapor pressure you can say, and this is the partial pressure of that element in steel under multi-component system. So, then this is defines the activity of that element is given by this. Now, so then you can write it also where I have written is there is the element as I, you can write it as I instead of writing the same, it is better to write so. Right. So, then partial pressure of I, vapor pressure of that element into the liquid steel, you can write it as Hi into Pi naught. And then activity you can write, that is the in terms of, if you want to write this activity, okay, and then there is the thing you can write simply with respect to the Raoultian standard state, you can, it is better to write it as Raoultian standard state, yeah, pure solid at the standard state. So, activity of I defined by this, and then you can write this activity is Pi is equal to your Ai into Pi naught, that is better. Okay, Ai naught, that is the activity of the element I, okay, with pure solid at the standard state, and then you can know that is the Henry's law is valid at the very dilute solution. So, in that case I can write it as gamma I naught Henryan coefficient into xi into Pi naught, right. And then xi also you can write simply like this, xi is you can write is a mole fraction. Mole fraction you can write weight percent of I divided by mi, okay. And considering the liquid steel contains, that is the around more than 95% is iron and least is impurities. So, and the total moles I can simply take, so the 100 divided by 56 plus summation of Wi mi, and those are the very small amount, that is why Wi mi, right. So, this amount is negligible compared to 100 by 56. So, if I just ignore that amount, so in the denominator, then I can simply write 0.56 of Wi by mi, right. So, xi you can simply write like this, xi is 0.56 Wi mi. So, if you know mi molecular weight, okay, if you know the weight percent, that is here weight percent, then you can calculate the xi, and Pi naught is known to you, and the gamma I naught also known to you, that is called the Henryan activity coefficient, okay, in the Raoultian scale. Henryan activity is coefficient in the Raoultian scale, and then it is the partial pressure of or the vapor pressure of the pure element I, and then you can simply write this is the your partial pressure of the element into liquid steel. So, finally, you can write this expression as Pi is equal to activity I, as I can write like this 0.56 and then Wi by mi, right, into gamma I naught xi into Pi naught. Bus. So, this is the way I can express, that is finally this is the expression you can write. So, here you can see for aluminum, you know the molecular weight 27 Pi naught is basically vapor pressure of pure aluminum is 2.66 milli atmosphere. These are all milli atmosphere, and the Henryan activity coefficient, okay, in the Raoultian scale is 0.029, and if you have weight percent Wi is equal to 0.05, that is the 8 into 10 to the minus 5, that is the, if your weight percent is 0.05. So, all the values are known, though, then the partial pressure of aluminum in liquid steel will be 8 into 10 to the minus 5. You can just simply calculate. And if you have weight percent of aluminum in the bath is 1 weight percent, okay, then this value is 1.6 into 10 to the minus 3. Similarly, you can see for manganese, if you see for manganese all calculation, you can find this value is quite high, that is 8.8 milli atmosphere at 1 weight percent. So, And 1 torr pressure is basically 1 milliatmosphere. 10 to minus 3 atmosphere means 1 milliatmosphere. So under 1 torr pressure, if we have manganese in the bath at 1 weight%, then its vapor pressure is 8.8 milliatmosphere or 8.8 torr. So vapor pressure of manganese is greater than 1 torr, okay, at 600 degrees centigrade, and it bath concentration at 1 weight%. Manganese bath concentration at 1 weight% at 1600 degrees centigrade. The vapor pressure of manganese steel is 8.8 torr. Okay, so under 1 torr pressure, manganese is easily vaporizable. That is, it will vaporize manganese because its pressure, vapor pressure is 8.8 torr, which is much greater than 1 torr. So it will form the bubbles and go away from the system because its vapor pressure is higher than the atmospheric pressure, that is 1 torr pressure. So manganese will, you can see there is it is easy to distill of the manganese at 1 weight%, but at lower concentration it may not be. That is, at lower concentration is 0.44, that is less than 1 torr, so it may not be distilled off. But at higher concentration, that is 1 weight% of manganese in the bath, it is highly suitable for distill off, that is the distillation. So manganese will be distilled off, right? Okay. So we can find from there, that is from this, that the manganese can be easily distilled off from the system. And other impurities like aluminum is not possible. For example, copper, nothing. None of them. There is a tin, silicon, manganese, copper, aluminum. Nothing will be distilled off simply. As element wise, they will not be distilled off. But manganese, as an elemental form also, it is possible to distill off the manganese when the manganese concentration in the bath 100%. Then you can easily distill off the manganese from the liquid steel. And so that's why that is the dust at the exit stream of vacuum chamber primarily consists of manganese and iron. Iron obviously will vaporize because iron has a large surface area, because iron is 95%. So under vacuum when you expose, then iron will vaporize, that is thing. And the manganese basically distills off because its vapor pressure is much higher compared to that of atmospheric pressure. So manganese distills off. That's why in the dust in the exit stream, in the vacuum chamber, there is a vacuum duct, that is which is exit duct. If you see the exit stream there, then you can find dust consists of manganese and iron. It is experimental evidence. Okay, besides also aluminum and silicon is also reported to vaporize in presence of oxygen and sulfur, because in presence of oxygen, aluminum forms the Al2O gas and then it forms the gas, so it can vaporize away. And then SiS gas, there is a silicon sulfide. So in presence of oxygen and sulfur, this aluminum and silicon also can vaporize from the system under vacuum, forming this type of gas, ALO gas, SiA gas, etc., SiO gas. Okay, so this is, and then now there are the different degassing practices are there. One is called the stream degassing, where basically you allow the liquid steel to fall in the form of a stream in a vacuum chamber in the form of steam, and then it is poured into a ladle. This is a ladle and liquid is from the top ladle is there, this is a vacuum chamber. So when the liquid is transferred from this ladle to this ladle, the liquid is exposed to the vacuum environment and the gas gets degassed. Okay, this is called the stream degassing. And then the ladle degassing is this. There are two types of ladle degassing is there. One is called your vacuum degassing. Okay, ladle degassing. In ladle also you can do. One is the vacuum degassing. Just you bring a vacuum chamber over the ladle and you can degas the system. Is called the VAD unit. That is the vacuum degassing system. Okay, and it is basically without any your what is that called, heating. Okay, so in this figure you can find that okay. This is the without heating, this is the vacuum degassing you can find. So your D1 heating process is there. Okay, so vacuum degassing means basically you just bring the ladle under the vacuum and then you, and with some with case of stirring is there, so you can do the vacuum degassing, but there is no temperature compensation, because when you are degassing you are stirring the bath, so your temperature will also lose. So that, because without stirring, if you do the vacuum degassing, there is a problem, the bulk, there is a, that is the, what is that called, the mixing will be very less. So stirring is very essential during the vacuum degassing, such that the elements from the interior of the bath can be transported to the interface, gas, ambient interface, liquid gas interface. From here they will be uh, they will be vaporized, right, or they will be going to the, they will be join the vacuum. So the thing is that, so that's why you have to make the bath, good stirring of the bath by the argon stirring and all these things. But during this process you will lose some heat. That's why you have some system which is called the vacuum arc degassing, where you can compensate the heat also by arcing. So this system is given here. You have the arc is there, and then you have a inert gas stirring is there, such that the bath is completely mixed, and the gaseous impurity can easily transported from the interior of the bath to the vacuum chamber, that is the gas liquid interface, and from there they can be degassed to the system, to the vacuum system. Okay, so those things are there. That's why stirring is very essential, and then you can find arcing system is there that can compensate the heat also. That is called vacuum arc degassing, and when there is no temperature compensation is called the vacuum degassing. After doing the vacuum degassing, you can take the ladle to a center where you can ladle furnace or somewhere we can compensate the heat. And another thing is there, and it's called the vacuum oxygen decarbonization. It is called the VOD process. It is called the vacuum oxygen decarbonization. That is called the VOD process. And here it is the vacuum oxygen decarbonization, that is the VOD process is here. Here basically you have both the inert gas stirring as well as you have oxygen lancing from the top. You can find you are giving the oxygen, and here is also inert gas stirring is also there. So as a result, this oxygen will react, oxygen will be coming from here, and this will react with the, and you can see this is similar to the oxygen lancing in the LD furnace. So as a result, they can form some kind of foam and emulsion, and where the decarbonization will be very fast, and then it is exposed to the vacuum chamber. So that reaction will move in the forward direction significantly. Okay. So there is a lancing from the top, oxygen lancing, and inert gas stirring from the bottom for complete mixing, and the whole system is kept into under a vacuum, and this is called the vacuum oxygen decarbonization, right? So you can oxidize the carbon by supplying the oxygen, and under vacuum you can bring down the carbon to a very low level, and not only carbon, oxygen both will be come down to a very low level. Okay. And then there are called the circulation degassing, that is the single snorkel system is there, and the double snorkel system. These are called the snorkel, and you can see circulation degassing means you take some amount of the liquid from the ladle into the vacuum chamber and then release them after they are degassed through this nozzle. So this is one snorkel, up snorkel, it is the down snorkel, and use some inert gas here is called the lifter gas. Basically argon is purged here, so that argon basically lift the liquid stew from the liquid bath to the vacuum chamber by buoyancy, simply by buoyancy or drag. So some lifter gas argon is there, and that basically pushes the liquid from the liquid chamber to the vacuum chamber, and then from vacuum chamber they automatically, when they are degassed, they become heavier and they can come down easily under gravity through this snorkel. So this is called a circulation degassing with two snorkel. Another is their DH degassing. It is called the RH process, and this is called the DH. In case of the DH, you take out some amount of the liquid metal into the vacuum chamber, and after treating it, they will come down through the same snorkel, right? So that way, that is called the DH. But this is not in practice. This is not practiced too much nowadays. The major practice is the circulation degassing with two snorkel, that is called the RH degasser. So it is used very much. Okay. And RHOB process is also, you can do that carbonization also. You have an supply for oxygen from the bottom. If you supply oxygen from bottom, then you can decarbonize the bath also very significant amount. Okay. So this is called the RH process. This is the steam degassing, this is the RH process, this is the DH process, this is your VOD process, vacuum oxygen decarburization, where basically oxygen is charged from the top, inert gas starting from the bottom, and whole system under vacuum. It is called the vacuum arc degassing. You can see arcing system is there for arcing and for temperature compensation, and the gas stirring is there, and whole system under vacuum. That basically you will degas the system. Okay, so this is the things is here. And this is called the ladle furnace. This is the ladle furnace. This is basically in 1 atmospheric process, and here no vacuum is there. And here you have an alloying addition, you have arcing system for temperature compensation and for the gas stirring. We will talk about that thing. This is an basically here it is an LF process. So all the process, if you write it, so you can write it here. So this is the steam degassing, this is the RH. Oh my God. This is the RH and this is the your DH, and this is the VOD, and this is your VAD, and this is the LF. Ladle furnace is also there. Okay. Okay. And this is the steam degassing. Okay. Now RH injection process, this is an RH injection process is a very versatile process. This is the RH process. You can see a lot of operations and then not only for degassing here. So degassing is obviously one of the major aim of the RH process, but nowadays you can do the decarburization by RH UV process, RH oxygen blowing, that is you can do the oxygen blowing here. In the vacuum chamber itself, you can do some amount of oxygen blowing. So you can bring down the carbon to a very low level. So you take out some liquid and then you can decarburize it and then it will come down. So you take out some amount of liquid into the vacuum chamber and do it. So this is the way it goes on. So you have a particular recirculation velocity. You can take out some amount of liquid and come down. So that way it is done. And then ultra low carbon steel, that is the thing. Very ultra low, there is IF steel you want to produce, you can do it into the RH vessels very easily. So this is the way it is done. And then you have the chemical heating and deep deoxidation. You can do the deep deoxidation, and if you need some here, no electrical heating, chemical heating, you can add some aluminum addition for chemical heating, and you can do the deep deoxidation, very deep deoxidation, because under vacuum it is possible. By oxygen blowing you can do the that is the deep deoxidation will also be done, right? And then you have desulfurization you can do. You can see this is the fluxing arrangement is there, fluxing submerged lands. Through the submerged lands you can add the flux along with the argon gas, so you can add the flux here, and obviously you have to flux should be for making a slag which will be highly reducing as well as basic. So you can use some carbide slag also. So it can be calcium carbide, and you can those powder can be transported through the submerged lands with the help of some argon carrier gas. Okay, so you have to add flux with the argon gas, you can inject it, and then you can do the deep desulfurization of the bath, and you can do alloying obviously. So this is the way you can do the alloying. So now RH vessel is used basically for versatile purpose. It is for degassing, it is for deep decarburization, deep desulfurization, and also alloying purpose. Micro alloying, you can do very sophisticated alloying like micro alloying in this. For example, IF steel, you can make it here. IF steel is nothing but very ultra low carbon steel with micro alloying. So in conclusion, we can see there is a solubility of dissolved gas, mainly nitrogen, hydrogen, oxygen in solid state is very small, and they produce very undesirable hydrides, nitrides, and oxides during solidification. Therefore, their amount in steel should be reduced to a very low level. Thermodynamically, hydrogen and nitrogen could be lowered even below the 20 ppm safely, but in actual practice, it is not. Kinetically, nitrogen removal especially is very difficult in presence of oxygen and sulfur. So you have to deoxidize and desulfurize the bath from very low level, very high level. There is you have to bring down the oxygen and sulfur to a very low level, then you can do the denitrogenation. Otherwise, oxygen and sulfur occupy the space on the surface and it restricts the aluminum, nitrogen desorption from the liquid bath to the atmosphere. So it is very important. And we have also seen there is the manganese distilled ops under vacuum, and therefore, if you want to produce an manganese steel, you must do the alloying after vacuum operation. After you do the vacuum, and then you at the last stage, you do the alloying. And the RH degasser is a very versatile unit in integrated steel plant, which could be used to produce ultra low carbon steel and gaseous impurity free steel. Very, very low level gas you can produce. So very ultra low carbon as well as gaseous impurities, or you can say almost gaseous impurity free steel. So these are the vacuum techniques that are used, and major vacuum techniques, as I said, in the steel plant are vacuum degassing, vacuum arc degassing, vacuum oxygen decarbonization, RH degasser. These are the most important or very popular degassing techniques that are used into the steel industry. Thank you very much.